So, as we mentioned in the last class that in the last class we talked about the observer problem, remember, and that was a simple problem in the sense that no noise, I mean lot of practical things were not mentioned, at least I mean they were not even considered to exist, and at the end we said that we have to, if we want to take care of these things, then we have to use the Kalman filter in practice actually. So today we are going to start looking at the Kalman filter. So what we will do is we will first describe the model and then we will start the derivation. I don't think we will be able to complete it today. There are many derivations of Kalman filters from various points. In fact, I mean Kalman wrote the paper in 1960, by the way, on which described the Kalman filter, and after that lot of work has been done, especially by Thomas Koilath is one of the scientists. He happens to be an Indian born also, visits Bangalore, used to visit Bangalore almost every winter. Incidentally, Kalman is very much alive. He is so anyway, that apart, so let us start talking about the model. So now this is the model, okay. This is the stochastic, actually it is mixed stochastic and deterministic. So compared to the previous model, slight change in notation, because now I am, you follow certain texts, so I mean unless you follow its notation it becomes difficult. So this xk plus 1, previously probably we were writing in brackets, so this xk plus 1 is the state at, now we are talking about discrete time models, we are not talking about, there is a continuous counterpart of the Kalman filter, that is called the Kalman-Bussy filter, we are not talking about it, okay. So we are talking about the discrete time Kalman filter, which assumes a model in this form, okay. So there are certain things to note here. Firstly, that I am assuming that the state matrix changes with k, so it is a time varying system. This is the general formulation of the Kalman filter. You can assume that all ak is equal to a. You can also assume a time invariant case, but the Kalman filter formulation is done for a time varying case. So that is why I have put these k's on the even the system matrices. So they are supposed to vary with time, okay, in a predetermined manner, right. It is not nonlinear, it is just a function of time, okay. Now apart from akxk plus bkuk, which were there in the observer also, now we have a third term, which is gamma k, this is I think xi or zeta, okay. If this I always get confused between xi and zeta, probably it is zeta, okay. So I will call it zeta. Is it zeta or xi? I think it is xi, yeah. So anyway, we'll remove that confusion. I'll check up in the dictionary. So this is let's say gamma k xi k. So here you have this is the term which is unknown. So we said that inputs, there are two sources of this uncertainty. Number one is that, see actually what is happening is that typically what is happening, that you have some, let us say some control computer which goes to the actuator, which goes to the plant, okay. So this is the control processor. Sometimes in aerospace technology this is called OBC, on board computer, which contains the autopilot algorithm, etc. So that gives a command to the actuator, and that gives the command to the plant, okay. So this is the, say, vehicle. So sometimes if you are using the input here as u, then that may not be the same as what is going here, number one. Even otherwise, even if you consider this to be the plant, you might consider that, even then there will be other inputs called disturbances, right, which will be unknown. So there are uncertain inputs. just to capture this, this term is included, this xi is unknown. Similarly, the output is normal Ck xk plus dk uk plus there is a measurement error. So, this is the measurement error term, right. All sensors will have measurement errors. Now, so these are the dimensions, x is n into 1, u is m into 1, xi is q into 1 assumed, measurement noise is p into 1, which means measurement is also p into 1. Once you put these, then you have corresponding dimensions of the matrices, right. So, this is n into n, this is n into m and all that. Now, the question is that unless you do some, if you assume it to be totally unknown, then you can't do anything, you can't get a result. You have to assume something, some bound on values, something, otherwise you can't obtain any result. So, therefore, we have to necessarily, we have to assume something about this. So, what we assume is in a stochastic setting, there are other algorithms. For example, there are H infinity filtering algorithms which will not, which will assume bounds on this, absolute bounds. Value of xi should not go beyond this, that kind of assumptions. But here we are using a probabilistic description. So, our assumptions are as follows, that these two are both 0 mean. So, this equal to 0 for all k. Can you read this? Can you read these lines on the TV? Okay. Second thing it says is that the correlation, in this case correlation and covariance are same because the mean is 0, is, so you see that they are mutually uncorrelated. So, if k and l, this delta is sometimes called the Kronecker delta. There are two delta functions. The continuous time delta function is called the Dirac delta and the discrete time delta function is called the Kronecker delta. This delta means that when k is equal to L, its value is 1, when k is not equal to L, its value is 0, which means that if these k and L are different, then their correlation is 0. So, the successive samples of noise, of the same noise, are uncorrelated, it says that. While obviously if you take xi k transpose, then you will get a matrix qk, which is assumed to be, it necessarily has to be positive definite, okay. Why? Naturally, because if you take x transpose this into x, it will be non-zero, it will be greater than 0, not only non-zero. Similarly here, so this is called the process noise covariance, this is called the process system noise or process noise and this is called the measurement noise. So, this is the process noise covariance and this is the measurement noise covariance at time k. Again we are assuming that their properties may also vary with time, right. But the process noise and the measurement noise are completely uncorrelated, they are identically equal to 0, even xi k eta k transpose is 0. So, even if k is equal to L, it is 0, so they are never correlated, okay. So, similarly the initial state is also considered to be a random variable and its correlation are also assumed to be 0. These you have to assume to, you know, unless you assume these things, then your analysis will become too complicated. So, you can't proceed, you can't get a clean result, okay. And in many cases, since these sources of noise etc. are totally different, so they are quite likely to be uncorrelated also. So, at this point of time, remember that I am not making any assumption that they are Gaussian or anything. You know, sometimes such assumptions are made in some proofs of the Kalman filter. So, but I am not making any such assumption, but this is what is necessary to assume, okay. So, nothing much, signals, I mean the disturbances are generally assumed to be 0 mean, right. There are three uncertain things, one is xi, another is eta, another is x naught. the initial state, which is unknown, which was unknown even in the case of the observer. And what we are assuming is that the xi and eta are 0 mean, xi is uncorrelated with itself, and they are actually independent of each other. So this is the assumption. So they are, they are like clean signals, and white also because they are uncorrelated. All right. So this is my model. Now naturally, now you see that it turns out that we can break this. This has one deterministic component and one stochastic component. So it turns out that we can really separate out this system, that is view this system as a sum of two systems. One is a completely deterministic one, another is a completely stochastic one, right? And the completely deterministic one solution is known, normal linear system solution. So there is no estimation there. So the estimation problem needs to consider only the completely stochastic system, which means that in our Kalman filtering problem we can ignore the input u. So it will get, so terms will get simpler. That's all. So I can look at it in this way. So if you write that the state can be seen, that is, now we are performing a decomposition. So this system state is supposed to be a sum of two states. One of them is deterministic. This is the deterministic system where there is no stochastic input, everything is known. Okay. Similarly, there is another system which is totally stochastic, right? It is totally driven by stochastic signals. There is no deterministic signal here, and if you take the state of this and the state of this and then add, then you get the total state. So you can just add these two and you will get the old equation back, correct? So then when we are talking about the Kalman filter, we only need to consider this we can ignore because this is a deterministic solution, no estimation needed. So this part has a well known deterministic solution, and the estimator needs to be based on this only. Okay. So we can ignore u for the time being. Step by step. So we have got our, now before we solve the Kalman filtering problem, actually I have, we have chosen a proof which is from a particular text by Chui and Chen, and it is a unique way of proving, and I mean I personally found it very easy and simple to follow. It's based on, I mean, common sense optimization approach. There are many other proofs, we can see some of them. So for example, there is an innovations based proof which will require concepts of Gram-Schmidt orthogonalization of signals, etc. There are some additional concepts which will have to be dealt with in. Here there are certain assumptions required which are again undesirable, that is correct, but let us make those assumptions and first see why the Kalman filter is optimal. Then if time permits, we can look at the Kalman filter from various ways. We can look at it as a Bayesian estimator which is seen to be as a conditional mean, or it can be seen as an orthogonalizing filter which actually makes the innovations white. So there could be various interpretations from which the Kalman filter can be derived under various sets of assumptions. We are looking at one of the approaches of proving the Kalman filter, which is very simple and does not require any extra knowledge, requires some assumptions, but will be I mean you will easily be able to appreciate that how it is optimal without any extra knowledge. So from that point of view, I have chosen this proof among many others which exist in the literature. So now before proving the Kalman filter, we are first solving a simple problem. The Kalman filter, actually the problem, the Kalman filter is supposed to give you a state estimate which will optimize, which will first of all take care of all past measurements and will minimize the variance of all those measurements with that estimate. So first of all, let us see that if we are given one value of measurement v at any instant vk, how to choose a state x, that is how to calculate and estimate xk such that the variance of that measurement is minimized and something else is minimized. So first let us try to solve the problem for a single measurement case, then we will try to solve the problem for many measurements, and that will give us the Kalman filter. So the first problem is much simpler. The first problem says that suppose this is your equation. So here you have a measurement, this is here you have a state. So Ck xk plus I have used the term xi k here for some reason, because it will come later on. In your earlier equation you will find this as eta k, but in this case we have used xi k. Okay. So suppose this is the true system equation, this is the true state, and the measurements are being generated in this form. This is a random process. Okay. Now what is my objective? First of all, I want to find an estimate. I mean, the moment I want to find an estimate, I mean that estimate will have to optimize some performance criterion. So I have to define some performance criterion. All estimates, all optimal estimates will be optimal with respect to some performance criterion. So what is my performance criterion? So my performance criterion is this. I have defined it like this. So you see, what is this? This is a weighted error. Vk minus Ck x hat k. Suppose x hat k is my estimate, then what is my error? Vk minus Ck x hat k. So I am calculating a variance of error, but it is a weighted variance. In between I have put a Wk. Some Wk I am choosing. So I have chosen a weighted estimation error with some Wk which is a priori chosen. For the time being, let us assume to be fixed. We will also see how to choose Wk in a second step. So we are going step by step. First we want to minimize this. We want to choose such an x hat k which will minimize this for some choice of Wk. Okay. So the problem is to compute x hat k. This argmin means you have to find out the minimizing argument of this function. So this function, so you have to find the minimizing argument x of this function. In other words, you have to choose x here such that this becomes minimum. This is a way of writing argmin. So now what do we do? So first thing we do is that we see what we have done here. What have we done here? Look at this. If you multiply, this is, see, I have from, it was defined like this. Now suddenly I am writing this. How? So what I have done is, now if you multiply this Ck transpose Wk Vk transposed, yeah, yeah, okay, this is correct. What is Pxwk is Vk, Vk if I put here, it will be, let us multiply this to this, then I will get x. Just one moment, let me see. Actually what I am trying to do is, I have to minimize this sum. I have to choose such an x hat such that this sum is minimized. So what is the trick? Trick is that you separate it out into two terms. Okay, one of them will contain this x, the other one will not contain this x. See that the second term does not contain x. So there is no optimization involved here. You are supposed to choose x. So this term is independent of x, and I have written this term in such a manner that this term is always greater than 0. So it is supposed to be a positive definite thing. Why? Because this is positive definite, Wk is chosen as positive definite. So therefore this is a positive definite matrix, and this is some matrix transpose x transpose this x. So therefore this is also positive definite. So this is a function, this first term can never be less than 0. Actually can never be less than 0. Now there is a question which I am expecting here, it is not coming, is that firstly, is this a scalar that I am talking, that that will be less than 0, greater than 0? Is this term a scalar? It is not a scalar, because this is not a scalar. This has dimension p. So then this is not a, this is a p by p matrix. So what do I mean by it to be greater than 0? So whenever I say that a matrix is greater than 0, I mean that it is positive definite, which means that if you choose any x, then x transpose px, which is a scalar, will be greater than 0. So whenever I say a matrix is greater than 0, I mean this. Okay. So this is in that sense, right? So this means that this matrix is a positive definite matrix. Now we were confused about, we can just multiply this straight away. Okay, if you multiply it, we can do it term by term. This will come. So let us not do it now. I mean, right now, if we get time, we'll do it. This will come. You have to just multiply this term by term. This will become x. This will become, let me see some of these terms. This is Vk transpose I. Vk transpose, there is a term Vk transpose Wk Vk. Oh, okay. This has been made into a whole square. That's what. Here, what is the term which is not involving Vk? Not involving x. There is only one term, that is Vk transpose Wk Vk. Now here that has become so long. How? Actually, this Vk transpose Wk Vk is here. Only if you take this I and then open out this bracket, then you will get Vk transpose Wk Vk. Why this term is added? Because this term is added here. This term is added and subtracted here. Actually, it will require a little algebra. And why it is added here? To make it into a whole square. To get it into the positive definite form. It's a manipulation trick. So using this term here, they have made it into a positive definite form. Okay, that is the whole idea. You can actually multiply it out and see whether term by term it cancels. Okay, it will. So the idea is that term 1 contains x and it is non-negative definite. Actually, it is non-negative definite. It can be 0. If in fact that is our solution. So then this is always non-negative definite and this does not contain x. So therefore this will always remain in the performance index. So term 2 does not have x. So therefore this function is always greater than or equal to term 2. Correct? Is it agreed or not? Nobody is following?
Term 2 plus something.
Term 2 plus something. So when will it become? So minimum it can become is when it is equal to term 2. When will that happen? When this is 0. When this is exactly 0. So that gives my solution of x. That gives the optimizing solution of x. Okay. So x is simply you take from here. So this should be 0. So this inverse this. Remember that when I am saying this inverse this, I am assuming that this inverse exists. So that is number 1 assumption, that this inverse exists. Need not exist, but we are assuming. So this is the weakness of this proof, that it requires some additional assumptions. The Kalman filter can be proved without these assumptions also, but we are using this proof because it is simple. So under the assumption that this inverse exists, otherwise you can't write this like this at all. So under the assumption that this inverse exists, this problem has a solution which is this. So this is the least square solution given the weighting matrix Wk. This is simple least square solution. Any least square solution will always be obtained like this. There is also another way of doing this. For example, you simply break it up, open it out, and then simply differentiate it with respect to x. That also will give the same thing. Remember, when we optimized FIR filters, we did that. So it is you can do either way. Either write it as a sum of squares and then say apply this argument, or you can simply differentiate with respect to x. That also will give the same solution. So now we have chosen, this is my solution for a given wk to that problem. Okay. Now the question is that I want to choose wk, because where from this wk has come, we don't want wk. Okay. So now we want to choose wk. Now obviously you see that if you cannot say that, for example, if you say that now let us choose a wk such that this becomes the minimum. See, this has a minimum for a given wk. So I will say that now which is that wk which will give the minimum of minimums. I can ask for that, but that in this case gives you a nonsensical solution. That will be, I mean, you will always get the minimum of minimum when you have wk equal to 0, because this is the quadratic form. So its minimum value is 0. When does that happen? When wk equal to 0. But then wk is equal to 0 does not get you anywhere. You can't get a solution from there. So therefore we cannot use that formulation. Rather we are using this formulation, that let us try to choose x hat k such that this one, the true state minus the estimated state. See, for any wk I can get an x hat wk, which is this. This x hat is actually a function of wk, right. So this solution is actually a function of wk. So what will be the final error between the state, true state, and my estimate? That is also a function of wk. So I can minimize that function. So I can say that what is that wk such that if I solve a least square problem with respect to that wk, then I will get the minimum variance of my estimate with the true state. That's a, in fact the Kalman filter is a minimum variance solution. It is a minimum variance estimator. So so now we are trying to bring in that minimum variance. So now what do we have to do is that you simply write it as a function of wk, and then you have to minimize it now with respect to wk, right. So now in this place we have already put that function. See, ck transpose wk ck inverse. So this into this multiplied will give you just xk, which is this xk, and this into this is your x hat wk, this function. So this is yours. So this is your function, and then finally you can take this ck transpose wk common here, then you get this common, and then you get this as xi k. So this is your error still as a function of wk, this minus this, it is still a function of wk. Now you want to minimize the variance of this. So what is the variance of this? Variance of this will be what? It will be expectation of this into this transposed, right. So you go on doing this into this transpose, minus minus will become plus. So on both sides you will get these two, it will be a symmetric thing if you multiply. So this into this transpose, so this transpose means A, B, C transpose is C transpose, B transpose, A transpose. So now first term you will get xi k transpose. So this is now what is this? Remember, this is expectation of xi k transpose. Can you read this? So this xi k, and when you do the transpose of this xi k transpose will come in the beginning. So this xi k transpose. All other matrices are constant matrices. So therefore the expectation operator will go straight in. What is expectation of Ax, where where A is a constant matrix, it is A into expectation of x. So if you take expectation outside, the expectation will go through all the constant matrices. Anything which does not contain a random quantity, expectation can be taken inside of that. So all these matrices are constant matrices, constant and known. So there is nothing random about them. So when you take expectation outside, that is this variance, the expectation will go right in and will settle here. That is, this is the only uncertain quantity here, only thing which is random. So the expectation will go right in. Yeah.
If the system is changing, how can we see that CK is constant?
System is changing, but remember that we are now, first of all, there are two answers to this question. First question is that system is changing, but it is changing in a known way. We assume that AK, BK and CK are known at every instant k. So there is nothing random about it. Second thing is that we are considering it at an instant k. Right? Right now we are trying to solve the problem at an instant k. So therefore our CK is constant. Correct?
Why did we choose WK? Why did we introduce that WK weighted coefficient?
Because we wanted to finally come to solve this. So we are doing it in two steps. We want to solve this, but we don't know how to solve this, so therefore we have first solved the problem and then we are choosing. This is just a way of proving, right? So I mean, remember that we are not using any Bayesian estimation, nothing. We are just simply using normal optimization, normal least square just simple least square optimization and matrix algebra. We are not using any statistics. We have not made any assumption that these things are Gaussian or anything like that. That is the advantage. I mean, you can follow these steps. After all, this is simply normal, I mean, algebraic manipulations that I am doing. Otherwise, I would require some theory. If I want to, for example, if you read some other, I mean, very well-known text, you will find that they will first prove some conditional estimation results without going into the Kalman filter, and then they will pose the Kalman filtering problem as a conditional mean estimation problem, and then apply those results, and then out will come those Kalman filter equations. That's another way of proving. But then you first need to know what I mean how to calculate a conditional mean.
WK is coming right from top and it's not changing. It is coming in as a
So far we have not changed it. You see, we are, so far first we have tried to see that if we choose a WK, how to obtain the optimal solution. That is very simple. Now we are finding, so then for every choice of WK, I will get an optimal solution. Now we want to minimize this, This is our actual, we want to find a minimum variance estimate of the state. That is our objective. So now we are saying that, okay, now of these optimal solutions, if I now change WK, which one gives me the best solution? So first I keep WK, obtain a solution, then look at it as a function of WK and then try to choose a good WK. I am doing it in two steps. Okay. So this is my variance, which now the question is, what is that value of WK for which this variance will be minimum? Okay. So that's does not appear immediately apparent. It's so now again this is all matrix algebra. So now what they are trying to do is, okay, that I want to express it as there are certain matrix algebra results. So I want to cast it in a form where I can use some matrix algebra results. I want to get the minimum value of this. That's what I want to get. So how do I do it? So first I say that since Rk is positive definite symmetric, so I can break it down. Remember that when we made coordinate transformations for the adaptive filters, we had made a coordinate transformation based on eigenvectors, and then we said that then it will become decoupled. So what we are saying is that any positive definite symmetric positive definite matrix can always be broken up like this. This is called a UDU transpose factorization of the matrix. This is always possible, a standard matrix algebra result. So these U's are called unitary matrices, where U transpose is, that is U transpose equal to U inverse. They are such matrices, and this is a diagonal matrix, and this is U. So if this is true, then I want to now, actually what I want to do is I want to, I can hear sighs because people are getting lost in matrices. That is the Kalman filter. You can't be afraid of matrices and derive the Kalman filter. So now what we are saying is that, so we have expressed, so this matrix can always be broken up like this. If it can be broken up like this, now I want to take a square root of this matrix. Now again, what is the square root? It is nothing but a notation. It's a symbol. So by square root of Rk, I mean such a matrix such that into that transpose will give me this matrix. I mean like a square root, like root x into root x gives you x. So in that sense. So if you have, so I want to find out what is this. Now you see, you multiply this by this, what will happen? That this, if you take this transpose, what will happen is that you will get U transpose here. Now U transpose is I, so this will become I, right? Then next you will get this diagonal root lambda 1 thing, next you will get U. Now this diagonal root lambda 1 into diagonal root lambda 1 will give you diagonal lambda 1. So you will get U transpose, diagonal lambda 1, these two matrices, U. So you will get Rk. So this is such a matrix that this into this transpose gives you Rk. So it is always possible to express Rk like this. Why I want to do that? Because then if I choose it in this form, if I choose another, if I call Q to be this matrix, this Rk to the power half transpose Wk Ck, then this whole expression, this whole complicated expression, this one becomes equal to Q transpose Q. This is why I took all the trouble of breaking up, then doing root over, etc. So all this trouble was done because the final variance can be expressed as Q transpose Q. That was fairly obvious, because you see this is a symmetric matrix, so this and this inverses are same. I mean they are transposes of each other. See, this is this side transpose, this side not transpose. Wk is again symmetric, so therefore transpose same, and this is symmetric. So it was in a symmetric form all the time. So we just sort of formally split Rk into a symmetric form and then said one part is Q and the other part is Q transpose. Nothing. It was already in a symmetric form. Only this was sort of, this itself is symmetric, but we broke it into a product of two matrices. That's what we did. So now we have got this result. So where does it get us? Now we use what is called a Schwarz inequality. See, finally what do we want to do? We want to find out what is the minimum value of this. For which value of Wk will this become minimum? I am looking for a minimizing solution of this by choosing Wk, right? So again I will express it into a part which contains Wk, which is square, and I mean that kind of a thing. So I will have to somehow find out that what is that part which contains Wk and is greater. So that is what I am doing now. So imagine that, for example, first of all see that this is greater than 0 always. Again this is a matrix. So when I say greater than 0, it means positive definite. Why this is greater than 0? Because again if you do x transpose this into x, it will be greater than 0. Why? because something transpose something, x transpose x is always greater than 0. So if you take, suppose you take x into q minus ps as a vector v, choose x in such a manner. So then what will happen? This will become what? V transpose v. So V transpose V is always greater than 0. It is because of this form. Whenever you have something M transpose M matrix, it must be positive definite. So therefore this is always greater than 0 for arbitrary PQR, PQS. Now if you choose, so now if you just break it up, you can always break it up. Here you will get a term Q transpose Q, you will get other terms. So the other terms you can take on the right hand side. I have not written the whole proof. And then if you choose S as this, you can choose any S, after all these PQSs are free, for any PQS you can do it. So if you choose S equal to this, then you will get this result. Can you follow this? If you break it term by term, what will you get? If you multiply this by this, you will get Q transpose Q. If you multiply this by this, you will get Q transpose PS. If you multiply this by this, what you will get? You will get S transpose P transpose Q. If you multiply this by this, you will get S transpose P transpose PS. So all the other terms other than Q transpose Q you can take on the left, keep on the left hand side, put all the others on the right hand side, and then put S is equal to this, then you will get this. So now Q transpose Q, this is a standard matrix algebra relation again. I hope you can understand it. So now we have to choose we have to map it with respect to this. So now we have, if with respect to this we have to map this. So what is that mapping? So that mapping says that you choose P is equal to this. These people have simply, by observation and by thinking people have found out. I mean, if you think hard as to how to prove, you will get it. So then people have found that if you choose P is equal to this, then you will get that P transpose P is this, and this will become this. See how it comes. P transpose P is okay. This into this will give you Ck, Rk inverse Ck. This half and half will become Rk. That is obvious enough. And now the interesting thing is that if you take this thing, then final form becomes this. Now you see what was your xwk? What was your x hat minus, let me just 1 second. Yeah, compare with here. Compare with this. Yeah, this one here. This P transpose Q inverse is becoming this. Now the interesting point is that if you put, suppose you choose Wk equal to Rk inverse, we are actually looking for choices of Wk, isn't it? So if we choose Wk equal to Rk inverse, then you put Wk equal to Rk inverse everywhere. So here you have Rk inverse. So Rk inverse and Rk will get cancelled. It will become I. There will be one Rk inverse left here. So this will be Ck transpose Rk inverse Ck, and this is Ck transpose Rk inverse Ck inverse. So this and this will get cancelled. So you will be left with only this, which is Ck transpose Rk inverse Ck. So which means that if you put Rk inverse here, then this expression becomes Ck transpose Rk inverse Ck inverse, and that is here. Which means that this quantity is nothing but the variance of xk minus x hat of Rk inverse. So now what do we prove? What have we proved? We have proved that variance of xk minus x hat wk is always greater than variance of x hat k minus x rk inverse. It cannot be less than that. Okay. So which gives me that which tells me that I have solved the first problem, that if I choose W as RK inverse, then I get the solution which minimizes this variance. So this is my solution now of that old problem. Now only thing is that fine. So I have solved the first part of the problem. Only thing is that I have done all that with respect to only Vk. I have not considered any past anything. But if I have to do the Kalman filter, I have to find a minimum variance estimate for, that is it should be something which takes care of all the past data, because all the past data is available. This is an estimate which does not take care of any of the past data. It only considers Vk, one measurement. But ideally speaking, if you really want to construct something really optimal, then it should consider all the past data, because they are available. So whatever information has to be extracted from there, you should extract that. So now we have to, so in the second stage of the problem, now that we know that how to solve this problem for one measurement, we have to see in the second part that how to solve this problem for which will optimize this kind of variance for the whole past at every instant. So that will turn out to be the Kalman filter. And incidentally, it may, let me again reassure you, in fact that it sounds a lot of jugglery with matrices, but this is an extremely effective algorithm. It has been applied very widely, gives fantastic results. You will find what amount of noise it can clean. So it is extremely practical and used in all aerospace applications. So it is not that, that is why it is so famous, because it works. Okay. So and in fact we will realize how it works, because at least on this particular thing, we, more than having a tutorial, because this is a recursive algorithm whose greatness you will only understand by writing a program and then running it on thousands of data points. You cannot do, you can probably do some theoretical kind of problems in tutorials, but you can never do it in tutorial because you need a computer for doing that. So we will have an assignment, I will formulate it, in which you will have to write a Kalman filter program and try it with different process noise, different measurement noise, and see how good or how bad it is. Okay, only then you will get some feel of the algorithm.
So how can we know that other than RK inverse, the solution of WK not converge to the optimal? We have chosen the WK is equal to RK inverse for the solution. How can I know that other solutions are possible?
Other solutions are definitely possible, but then we have proved that if you choose any other WK, you will get higher variance. That's what we have proved, no? So we have found, that's what we have proved in the last step, that variance of xk, this one for any other choice of WK is going to be larger than this one. So you cannot find a WK which will give you a variance. You cannot find a WK and then solve the earlier problem which will give you a variance less than this one. That's not possible. Okay. So that's, here we stop, and in the next class we will consider the second part of the proof, which will be the